Yesterday we had our introduction to chemical bonding. We talked about the different types of bonds that we have. The covalent bond, which we separated into two types, a nonpolar covalent, a polar covalent. We talked about ionic bonding, and we talked about how to determine whether something was an ionic bond or a covalent bond. Bless you. Today we are going to begin our discussion on the electron dot notation. The electron dot notation uses the symbol of the element with dots placed around the symbol in certain spots. These dots will represent the valence electrons. Go ahead and take out your periodic table. We're going to be needing that, so grab that, have it handy. Okay? The valence electrons, remember, are the electrons on the outermost energy level. Electrons on the outermost energy level. Here is the dot pattern that we will use. So, if you would, just copy that down and then we'll explain it. Notice that the dot pattern only has 8. And we represent the first 2 on the right-hand side of the symbol. Then we go to top, and we rotate with the 3, 4, 5, 6, 7, 8. The first 2 go on the right-hand side, and then we rotate top, left, bottom, top, left, bottom. Now notice that there are only 8 places to put dots. That is because we are only going to be putting these dots on main group elements. What are main group elements? We discussed this yesterday. What are main group elements, Chloe? S and the P block. So let's look at just, because energy level number 1 is different because it only has an s orbital. Let's look at energy level number 2. How many electrons are across that energy level, if you would count them? How many? Energy level 2? 8. Thank you. Okay, I thought we were having trouble counting today. 8. All right? So there are 8 across there. If you look at any energy level, look at number 6. Okay? Look at number 6. We're talking only about the S's and the P's, right? How many are across number 6? 8. Okay? Now, where did we say that we have a full outermost energy level? At what group of elements? Not the halogens. The noble gases. Excellent. That's group number 18, right? So group number 18 has a full outermost energy level, and that corresponds to 8 of the S and P electrons, right? Now, these 1, 2, 3, 4 through 8, 1 through 8, represent this, folks. Okay? An s orbital, a px, a py, and that's a z right there. It looks like equals, that's a z. Okay? Px, py, this guy right here is pz. So if we think like this, okay? If we think like this, s orbital, right? How many electrons can an s orbital hold? How many electrons can any orbital hold? 2, okay? So here's an s orbital. Here's a px, right? How many can px hold? 2. How many can py hold? 2. How many can pz hold? 2. Now, I want you to jump back, because if you look at your numbering system, we went 1 here, 1 here, 1 here before we doubled them up, right? Go back and look at Hund's rule. Find Hund's rule in your notes. We discussed that with our electron configuration. What's Hund's rule say, Kane?
Orbitals of equal energy are each occupied by one electron before any orbital is occupied by a second electron. And I don't know what that says.
Okay. It says that orbitals of equal energy, these are all p orbitals, right? They all have equal energy, are occupied by one electron first before we double them up. So does that now make sense why we come a 3 here, a 1 here, and a 1 here? Because this represents px, py, and pz. So that is why we put 1 dot at the top, 1 to the left, 1 to the bottom, before we double them up. Hund's rule. So, I look at carbon. Carbon has an atomic mass of, an atomic number of 6, correct? Now, look at your periodic table. You're going to want to say that carbon has 6 valence electrons, but that's an incorrect statement. Okay? It has 6 protons, it has 6 electrons. How many of those electrons are on the outer energy level? Only 4, right? I'm going to give you a little hint here, folks. I'm going to give you a little hint with the main group elements. If you count across from left to right, whatever group, for instance, the alkali metals are the first group, right? How many valence electrons do they have? 1, okay? Let's look at our halogens. What group are they halogens again? Number 17, okay? How many valence electrons do you think the halogens have? 7, okay? Does it matter whether it's chlorine or bromine or iodine? No, they have 7 valence electrons. So if we look at carbon, and we count that it is 1, 2, 3, 4 over. So how many valence electrons is carbon going to have? 4. If you are going to draw the dots for those 4, go ahead and just practice. Follow that number scheme and draw carbon. See if you can do it right. Draw carbon, see if you can do it right, following your dot scheme. If you do, you should have something that looks like that. Okay? Now, if you have that dot right here, this dot a little bit higher, that's fine. That's fine. But you should have something like that. Now, what does this actually represent? Carbon has these 4 dots around it. Each dot represents an electron. Now, if we look at our electron configuration, if we make it for carbon real quick, it's going to be 1s2, 2s2, 2p2. Correct? 1s2, 2s2, 2p2. Now, these 1, 2, 1, 2, these 4 electrons are the only valence ones. This is an inner energy level, not a valence level. So that is why we have only 4, and we do not count the number 6. Okay? So our highest occupied energy level is what energy level? What's the highest one occupied? Energy level 2. Does it make sense why there's only 4 valence dots there? Got that? Give me a thumbs up there. Yeah, yeah. We're thumbs upping. Okay. Let's go back. See this? Okay? See this? What is the rule for valence electrons? The outermost energy level, correct? So, this one, I'm looking at 2 energy levels. There's the first one. There's the second one. Is the second energy level filled? Is the second energy level filled? No, because it only has 2 on the P, not 6. Okay? Is the first energy level filled? Yes. Okay? So, as I'm looking, 1 energy level, 2 energy levels. What's the outside one? Number 2. So, valence is outer energy levels. That's why we do not consider that one a valence level, because it's already filled, it's on the inside. Could I have this number, would this still be considered valence if this wasn't 2, if this were 6? Even though it's filled, would that still be considered the valence one? Let me ask you this. Is that the outside one? Yeah. Even though it's filled, it's still the outside one, so it's still the valence one. Okay? So in this case, we would have 8 valence electrons. Can we have 8 valence electrons? Absolutely. Absolutely. Now let's look at another one. Let's look at sodium. Draw your symbol for sodium. And how are you going to put the electron dot notation for sodium? How many valence electrons does sodium have? 1. So do you mean to tell me that it's as easy as just putting 1 dot? Yep. Where are you going to put it? Where number 1 is, on the right side. So, right there is sodium. 1 dot on the right side. It's that easy. Just have to remember the order. Now remember that it symbolizes an electron configuration. Now look at this one. How many energy levels do I have listed up here? I have 3, right? I have 3. Here is the first one. Here is the second one. And here is the third one. What is the outermost energy level? Number 3. How many electrons on number 3? 1. Do I include these electrons? No, because they are not outer electrons. So 2, 4, 10. These 10 electrons are not represented by any dots. Are they still there? Yes, because they're part of sodium. Okay, they're still there. It's just we don't represent them by dots. Okay, that's just what I explained to you there. Okay, the highest occupied energy level is 3. So 3s1 represents 1 valence electron, so we have 1 dot. Now, ions. We talked about ions yesterday. What kind? What type of ions do we have? Okay. What type of ions do we have? Anybody remember an ion? What are they? John? A cation is one and an anion is the other. A cation is a positive ion, an anion is a negative ion. Okay? So when we have ionic bonding, we have ions. Now, if you remember, anions are negative. Okay? You've already got this slide, folks. This is an old slide I brought back. So don't copy it again. We're just going to talk about it a little bit and refresh it a little bit. Okay? When an atom gains an electron, it becomes negatively charged, an anion. Okay? Nonmetals want to gain electrons. Metals want to lose electrons. We talked about that yesterday, maybe. Okay? So, anions gain electrons, become negative. Cations lose electrons, become positive. Okay? We talked about little anion and the plus cat. Remember that? Yes, yes you do. Now, cations are smaller, ionic radius. You remember that? Okay? Cations are smaller because they are losing an energy level. Anions are getting larger because they're getting the electrons spread out further on energy levels. Okay? Now, if you look right here, here is sodium. How do I know it's sodium? 11 protons. Right there, it says 11 pluses. I should have 11 minuses, right? Now, how do these elements want to achieve stability? Rachel? Okay, it's going to lose an electron because when it loses this electron, it fills this energy level. Understand that? By losing that electron, it gets rid of that third energy level. And is the second level filled? Yeah. Okay? So, sodium's more than happy to give up an electron because that's going to be easier. What's the other alternative? Gain 7? Which is going to be easiest? The path of least resistance to lose that 1. So, once again, sodium shoots that 1 out of there. All of a sudden, we don't have that third level. We now have a filled valence level, correct? So, I have sodium losing 1 electron. If you count up the dots representing electrons, you have 10. Protons are 11. You have a net charge of plus 1. Once again, here's chlorine. Chlorine's outermost energy level has 7 on that. Is chlorine going to want to lose 7 electrons? No. Makes more sense for chlorine just to gain 1. Okay? So, chlorine with 7 is going to add 1 electron coming there. Where do you think that electron could possibly come from? Okay? In this talk we're having, who would give it? Sodium, right? Because sodium wants to lose 1. Chlorine wants to gain 1. So doesn't it make sense that they match up together? Yeah. Yeah. So here we have the chlorine just got that 1. Now, if you look right here, here is sodium. Right? Its outermost energy level has 8 of them. Here is chlorine. How many does its outermost energy level have? 8 of them. Right? So when we're dealing with the electron dot notation of ions, it's a little different. Because I look here. Here's sodium. And sodium has one dot, correct? Now, to make an ion, sodium does what? Ships it out, loses it. So, I could do sodium like this, signifying that it is a plus charge and lost one electron like that. That's how I would do it. Now, would I count it wrong? Would I count it wrong if you had sodium like this and said that you had eight valence electrons with the plus one charge? I couldn't count that wrong either, because when it lost that electron, it lost that energy level. Therefore, its outer energy level had 8 of them. Okay? Now, chlorine's a different story. Chlorine's a different story because chlorine has 7 valence electrons. However, when chlorine is forming an ion, it gains 1 electron, doesn't it? So chlorine has gained an electron, and I'm just using different color to represent that 1 gained electron. So if I'm drawing the electron dot notation for chlorine, I have to have 8 dots around it, in parentheses, the little brackets there with the negative charge, signifying that this has indeed, that negative charge says that I have gained 1 electron, because now I have more electrons than I do protons. Does that make sense with the ions? Okay. Now let's just I don't know what my next slide is. Oh yeah, here's calcium. Okay, good. So I was going to say, let's try something different, one that has more than 1. Here's calcium. Here's calcium. Here's chlorine. If I'm going to draw the electron dot notation for calcium, calcium has how many valence electrons? 2. Now, do you think calcium is going to want to gain 6 electrons or lose 6 electrons, or lose 2 electrons? It's going to want to lose 2. Okay? Now, does it make sense then that it would give 1 electron to one chlorine, 1 electron to another chlorine? Does that make sense? Yeah. Yeah. So when we deal with these chlorines, they each want 1, right? They each want 1. Well, wouldn't it be real nice for this calcium to come up and say, all right, chlorine, I'll give you my 2. Now, what's his charge going to be? Plus 2. Because he's gotten rid of 2 electrons, and each of these chlorines will be minus 1. What is the net charge, though? What is the net charge if I put my calciums and my chlorines together? 0, right? Because I have 2 chlorines, each with a minus 1, and I have calcium with a plus 2. That's ionic bonding right there. Okay? That's ionic bonding, the transfer of electrons. The transfer of electrons. Any questions about this for me? Kane, shoot. Group 14. All right, you're going to see, we're talking about the carbon family, right? Okay? That's a great question because how many valence electrons do they have? 4. So they could lose 4, they could gain 4. All right? I'm telling you right now that group 14, the carbon family, which only has one nonmetal, right? It has one nonmetal, 2 metalloids, and the rest are metals. You're going to see that carbon is one of the heavy players in covalent bonding. Okay? Carbon's not going to gain or lose electrons. I'm trying to remember if I've ever seen the carbon plus 4 or the carbon minus 4 ions, and I can't tell you that I have. I can't tell you that I've ever seen that because it covalently bonds so much. So basically, what I'm saying is group 14 there doesn't want to gain or lose electrons because, you know, that's a pretty good distance both ways. So he's going to share. He's going to say, let's just share instead of gaining and losing. Okay, great question. Any other questions? Okay, now